Hey, welcome. In the context of a current blog post, I want to look at how to write good worker code for Camunda Cloud. And especially interesting is to look at using blocking or non-blocking code or using reactive programming or not. And in order to make that a bit more tangible and also to basically to prove certain things, I wrote a bit of code, which is here in GitHub. I added a very simple REST server, which basically just can get a REST request, sleeps for 100 milliseconds to basically like a latency in the network to simulate that, and that's it. Okay, so this is running in the background, and then I added a couple of workers in different languages, and I start with the language I'm most familiar with, which is Java. So it's relatively easy. So one thing I can do here is I can start some process instances which I want to work on. The process is very simple. It's this one. It just kicks off, and then we can work on that service task. In order to do that, I want to start the process instances like beforehand and not yet work on them. So I comment out any worker in Java. And if I have that, I have that in my favorite IDE. So as soon as I have that, why didn't it update what I did in the other thingy? That's weird. Anyway, so let's run this. So what that quickly does is just starting 500 process instance. It does that, by the way, in a blocking way. So that's the blocking API. This is because I want to avoid getting too much back pressure. If I do that asynchronously, I bombard CB with a lot of requests and will experience back pressure, which is a normal behavior. That's something for the next blog post probably to explain. But I don't want to have it, and I don't care about performance and parallelism of this at all at the moment. I don't care this. I just want to get it done. So I leave that running in the background, and then I start this again with a worker, and this is finished, by the way. Let's do a blocking REST call first. I don't have to start them again because that influences again performance. Hang on, nope, here. I do a blocking REST call, so I invoke the REST call. I use the REST template from Spring, hand over, basically call my little API. Then I log something that I'm done, and then I call the CB API, the Workflow Engine API, to let the Workflow Engine know I'm done with that task. And the join here means I'm now blocking to get the result. And then I'm increasing my counter that the job is finished, and I again do some logging. Okay, so I can quickly run this. Let's take a sip of coffee. And what you can see is, that's pretty interesting. You see a couple of threads actually working here, and they all complete jobs. So what you can see is that we have 1, 2, 3, 4, 5, 6 threads. Oh yeah, there are the numbers. 6 threads running, invoking REST calls. Then these sticks are basically waiting for the REST call to come back. And you can see the 100 milliseconds delay in here. And only then we can call the complete job in CB, and then we see that they're really completed. And as soon as they're completed, this thread is free to invoke the next REST call here. Okay, so what you can see, it's basically, in a way, sequentially. We just push that to 6 threads. Why is that? Why 6 threads? Because the worker internally can use a thread pool. So I configure that here. I use a thread pool of 6 threads. If I configure that to be 1, and let's see if I already used up all the 500 instances. Yes. Then let's start again. Let's say 100. We don't need that many. So I start this. I don't start the worker yet because I want to delay that till I'm actually ready. I should have done a different program. I just run in the background. But I was too lazy. Actually, I wanted to save the time spot to make this recording. So I was a bit lazy in certain things. Okay, so comment that again, comment that out, and comment that in. So I do the same thing again. I rerun the worker with a blocking REST call. And what you can see now, and that makes it pretty obvious what's happening here, is we're using blocking API. So we're waiting until that REST request comes back, right? So let's do this. Waiting. Where's the first one? Waiting for the REST call to come back with 100 milliseconds. Only then we complete the job. We wait for this to happen, and then we invoke the next one. So there is no parallelism here because I use blocking API, right? Okay, you can somehow tune that by using a thread pool, but that's very often not super easy to configure and to sort out the right number of threads. The other way of writing a worker is using reactive programming or non-blocking calls. And therefore, the code looks a little bit different. In this case, I'm not using the Spring REST template, but the Spring web client or webflux, how it's called. Within the Spring framework, you can use whatever REST client you want to. JAX-RS also can do a reactive API. And now I define my, my call, right? But now I'm not blocking to get the result, but I'm basically subscribing for the response, and can also specify what happens in the exception case. And if I get back a response, only then I'm now completing the job. And then again, I'm not joining, I'm not blocking for the result, but I specify what should happen when this is finished. And in this case, I want to increase my counter that I just did the job, right? And in case of any exception, I want to rethrow that exception. That basically leads to a retry within the workflow engine. That's not super important here, right? Okay, and the interesting thing now is that this has a very different behavior. And I should have started 500 the first time. Anytime you try to make a shortcut, it takes you more time later on. Sorry. So let's run this. Let's get another coffee. So I start these. I already prepare my code here. So as soon as I'm ready, I can start this. And no worries. You could do also starting more efficiently. That was not my goal for today's blog post and today's session. And I wanted to get my coffee done. Okay, cool. So let's restart that and go into the non-blocking worker for our REST call. The REST, this is the connection here, right, to the service task, by the way. And you see that now a different pattern is at play. So we already completed our 500 and the remaining 46 from earlier on relatively quickly. What you can see also is that now we're doing that with one thread. The same thread invokes all the REST calls, but it doesn't block for it, right? So it's really quick because we're just sending over the request, or we put it basically on the wire, we put it in the buffer for the wire, or whatever the implementation is here. So it's really quick and efficient. We got our 32 jobs queried from the workflow engine, and we basically just need a couple of milliseconds to push them all out, right? And then we're waiting for the response, but we're not blocking anything. We're basically in kind of a subscription mode. So whenever we get a response, this is picked up from the network, And then as soon, and you can see that we're now in a completely different thread. As soon as this response is picked up, it's processed and basically goes into the callback here, and it completes the job. But again, it's not blocking. We will see that in a second. So we can do all of these and already starting invoking more REST calls and here, right? So no, where is it here? And here you can see it's again another thread that is actually picking it up. What you can also see is that there are thread pools involved. So the basic idea of that reactive programming is that it can execute stuff in a loop. So even with one thread, you can do a lot of things because you're not blocking for things. Whenever you're waiting for I/O, which is kind of the long times you're waiting, you're not actively waiting. You're basically kind of in certain queues or whatever. And whenever the response comes back, the callback is activated, and then you start computing again. So this would also already be very efficient with just a single thread. But underneath all these reactive applications, in this case, in the Java platform, there are a couple of thread pools by default, which are actually very efficient and which are leveraged here without you actually knowing or the need to configure them. They try to maximize how many of these so-called tasks they can execute on certain threads. So you're not really looking at threads or cores. It's totally abstracted from you. And that's a pretty powerful programming mechanism, actually. And if you look at the throughput, and it's a very basic way of calculating that. So I was not looking after getting numbers here, but just that you get an idea. So here we're getting around whatever, 60, 65, 90, 80. So this is kind of the throughput of jobs per second we can execute. At some point in time, we had 120, which is quite a lot, actually. So 80 or 70 or 60 looks more normal on my machine. And what you can also see is that we even had too much load on my nice little REST server. So sometimes you refuse the connection. Which is quite a thing to exceed them, which is not a big problem because that just means we retry it in the workflow engine details. So what you definitely can see is that the throughput is much higher with that reactive programming style, and you don't have to care about thread pools at all, which is also normally a big advantage. Okay, if you're not so much in Java, I mean, you can just download it, try it yourself. Just create I'm running against Camunda Cloud here, by the way, so you can just create a Camunda Cloud cluster and do that yourself. If you're not so much into Java, I did the same experiment also in C#, for example. So in C#, it's more or less the same thing. So I create a CB client, I start process instances. This way I do that blocking when I start up. And then as a next thing, I either start a blocking or a non-blocking handler. And that's really the same thing as in Java. So I could have a blocking handler saying, okay, I now do the GET request, and then I block for the result. And I do the complete command, like the service task has completed, and then I wait for that to happen, and then I move on. And then it's really the same behavior. I can quickly show you that. Blocking, so we want to do blocking. So we are in .NET. .NET run. So this should start in a second, actually. So let this run in the background, and let's keep looking at this. So you will see the same pattern as in Java, basically. And then you can do, obviously, also a non-blocking version of this. So more space here. Where is it here? So this is actually the normal way of using it. I doing a GET request, and then I have kind of a future promise and closure. I always mix up these terms. I'm super sorry for that. But basically, you specify what happens when the GET request was successful. So I get a response. Oh, I typed any key to stop. That's pretty bad. Let's do this again. Yeah, and let's not start so many instances because we already have them. So where was I? Continue with. So I get a response, then I log, and then I complete. Again, I continue with that callback when the complete job command on the workflow engine was processed. Do I have my Java worker still running? Yeah, this one might steal all the jobs from the .NET worker. That's pretty bad. I was a bit confused that nothing is happening, so let's do 50. Sorry that this takes a bit, but no. So you can see that, again, invoke REST call, finish, complete job, completed. Invoke REST call, finish, complete job. No, so you see the, again, pretty much the sequence here. Why is this one before? That's interesting. What's my counter method? I'm sorry. Counter inc. That should come before actually. This is Java. That does make sense to look into Java when I'm looking at the C# code. The inc. Huh. This is interesting. It's a little bit puzzling to me at the moment. I try to figure that out later on, okay? Promised. But you see that it's pretty sequential. Okay. That was what I wanted to show. Now let's do the non-blocking version, which is kind of not very surprising. We already looked through the code, so I can do this. And we will more or less see the same pattern as in Java. Now we're having a thread pool that's basically handling it, which is kind of in one of the abstractions underneath of the platform. We're getting much bigger throughput actually. We're getting up to 100 here, which sounds a lot, but yeah, maybe we got that. But as you can see, it's pretty quick actually. Okay, cool. So let's stop this, and then the last one, and that's an interesting one. I'm going to the JavaScript version. Same thing. I create a client for my Camunda cloud. Then I start a couple of process instances. Let's make 100. That's quicker. And then I either start a blocking or a non-blocking worker. Let's start with the non-blocking worker. This time I'll tell you why in a second. And the non-blocking worker is kind of what you would expect. So invoke the REST call. I used Axios, but you can use, again, every client library you want to use for doing REST calls. Use the get and then define the callback, what happens if I get back my response. In this case, I just complete the job within the workflow engine. And again, I define what happens if that is successful. I increase the counter and do my logging. Cool, easy peasy. Let's run this. So it's kind of what we expected. Everything is happening in parallel. We're getting up to 40 instances or jobs per second. But again, if it's 40, 60, or 100, doesn't matter too much. We're getting kind of real parallelism, and we can see that. Now let's switch to a blocking version. And this is this one. So in this case, again, I wait for certain results before I finish. And this is kind of the homework. You can probably explain that to me. I haven't yet completely digged into the root explanation from that, but the behavior is a little bit different than you would expect from what you saw with C#, meaning that the behavior is still parallel. So it's still non-blocking. So actually, the implementation underneath how that works is totally non-blocking in JavaScript. And I think that's totally related to JavaScript being single-threaded for certain things and using a lot of these like event loops or processing loops internally. So they can't really do blocking behavior in that sense. So basically that means if you write a worker in JavaScript, you're safe anyway, in a way. But it's JavaScript. Okay. No, that's it. That's what I wanted to show you quickly. Thanks for watching. Play around with it. Have fun with it. If there are any questions, any feedback, anything I explained wrong, which might totally be the case, happy if you reach out. Happy if you give me feedback. See you around. Bye-bye.